Oh, come on, nobody jumped. Isn't that so interesting? These three most important numbers in mathematics, E, a transcendental, pi transcendental. I is not even a real number. But when you combine them in this very special fashion, you get something that's simple.
That's so exciting.
It is. I thought so too. In fact, this is so important. Can I give it a name? I'll call it Euler's constant. Very nice. Or how about Euler's identity? I can spell identity. Euler's identity, yes. I can prove that this is true. I can prove this thing equals. I just need a tad bit more material. I need the topic of power series expansions in Math 31 to prove to you that it really is the case that this beast is equal to this beast. I'm sorry. I just can't prove it yet. I need that powerful machinery of the integral calculus. I didn't mean integral calculus. I meant power series.
When will you learn that?
Probably 3/4 of the way through Math 31. But it's got a really nice consequence, doesn't it?
All of calculus equals -1.
Oh, calculus equals.
I thought the number was 47.
You mean 42.
Oh, 42. Was it 42? I keep saying
Yeah,
47.
42 is the answer to the question universe.
For some reason, I'm thinking it's 47.
What's that?
What's the question?
I don't know. That's why they built the planet Earth as a computer.
That was great.
We're talking about science fiction novel.
Who's actually read that? It's Douglas Adams.
No, what's the author's name? Abbott?
Douglas Adams.
Douglas Adams. Excuse me, Douglas Adams. Yeah. I never heard of that book. Like a few summers ago, my wife bought me the entire collection of all of them. My gosh, I couldn't put it down. It was so interesting.
British humor and science.
Don't see the movie.
No.
It's like going to see Flatland. Don't even do it. It's not worth it.
There is the BBC TV series is pretty good.
Yeah.
The BBC series for what?
The BBC did a TV series back in like the 70s or 80s. That was pretty good.
On Hitchhiker's Guide to the
Yeah, they
Galaxy?
do the entire series, but they actually accurately do the series. It's really low budget, but it's a lot better than the
I
movie.
did not know that.
Yeah.
I really didn't.
Yeah.
Wild time to get obsessed on something.
Yep.
I've never come across that. Huh. Is that on Netflix?
Yeah, it should be.
Wow, I'll check it
Yeah.
out.
You won't be grading tests. You're gonna get points.
Be sure you watch it during summer. A lot.
Oh, come on, you guys, humor me.
3x squared.
What can you say about the derivative with respect to x? Of x cubed plus any constant c?
3x squared plus c.
Nope.
Well, going in a direction then. Maybe we can say this. If I want to undo the differentiation process, I got a whole new collection of symbols. I will use a really big S, followed by 3x squared. And sometimes I'm nervous. I'm nervous this may not be the variable I'm really intended on using, so I sometimes classify the variable to which I pledge my allegiance for undoing the differentiation process. And the process of removing this big S with a dx notation is just listing what the heck the antiderivative is. How many antiderivatives do I have? Infinitely many. And so when it comes to this big S symbol followed by a function followed by the symbol dx, it just means I'm trying to proclaim the infinite collection of antiderivatives for this function, which is nothing more than a bunch of stuff whose derivative is in this position right here.
Is there some history behind the S symbol? I mean, did somebody just kind of throw it up there and say, hey, let's just...
Doesn't matter.
Yes.
Okay, all right.
Yes. When it comes to definite integral, you're going to see that I'm going to use the upper Greek letter sigma, and it's sort of like I'm just extending that, taking the limit of it. You can almost see that stretching it out, and I'm using the big letter S for that.
I thought it was just somebody's handwriting, some mathematician's handwriting. That was
You can treat it as such.
Isn't sigma for some notation?
Oh, maybe I'm wrong. Sorry. Is this the Greek letter sigma?
The lowercase.
That's lowercase.
It is lowercase. Why don't I use that?
Because it'd be confusing.
Because statisticians stole it and used it for
Some
standard
notation.
deviation. All right, so I'll choose the uppercase Greek letter sigma instead. And I'll get into that, I promise. Actually, I'll get into that tonight.
Why
Maybe not as far as Riemann
So
sigma.
is there a big difference between that and what you'd use for like standard deviation?
Oh, huge. This simply represents some kind of statistics value that measures dispersion of data away from the mean. This is sort of like taking the big sum of things. This is like adding a bunch of things together.
Okay.
I'll get more tight on that notation tonight.
So why DX rather than D?
You know, what a good question. It's because sometimes in the integrand's position I might have different variables. It's just that this is the variable in which I want to undo the differentiation process.
Just that, okay.
Matter of fact, you guys check this out. Back in the 3rd grade, what did you call 3?
3.
You did not. You called it error. You called it a,
Constant.
or maybe a,
I don't think we're smart.
A number?
an addend. An addend. What did you call it?
What kind of 3rd grader
What did you call it?
Subtrahend.
Subtrahend. Thank you. What do you call it too? What? Am I speaking to the right? Did I walk in the right room?
You have a really high expectation of 3rd grade.
I told you the story of my 5th grader, right?
Yeah.
Writing on the wall.
Oh, yeah.
Okay. What do you call it too?
Radicate.
A radicand. Oh, I got an idea. I'll call the 3x squared a integrand. Use the same stuff.
You made that up.
I'm going to go home in a minute. I'll call the symbol my integral symbol. And I'll refer to the whole thing as an integral. And the process of evaluating an integral is nothing more than the anti-differentiated was in the integrand's position. Integrand. That would
It
be
looked like Instagram, but with numbers.
Not an Instagram, no, that's not what I meant. So the whole thing is called integral. You guys see the car on the road, right?
The one that says Dolly guys?
No! You've seen the Countess cars on the road, haven't you?
The what cars?
No? Oh, you haven't, you mean these ones.
Oh,
An
Integra.
But if you look at the Integra with the luxury edition,
No, let's not bring cars out.
you just really know about cars. Is they don't use a symbol for the infinity? That's so disappointing.
They
I'm
also
serious, I really know about
They
it.
also don't spell it right. So
Yeah, they don't spell infinity right.
They spell it with an I.
Yeah.
Oh, you're right, I never thought of that. I don't have an infinity, I never thought of that.
So exciting.
Okay, you guys, let's play. I think to differentiate x to the n power, I get the, you took too long, you deep RES. So, let's talk about dividing both sides by 1 over n. You guys help me with this. Is my math D skills okay? No? Why not? I just divided both sides by n.
You question, that's what I'm saying.
Oh, gotcha. No tricks, is that okay?
Yes.
Yeah.
Oh, by the way, that's just a coefficient in terms of x. Can't I bring it inside the differentiation process? Oh, hold it. And if you guys allow me to make a substitution, if you guys allow me to let n minus 1 be called something, I don't know, something more simplistic, then I think on the right-hand side I've just got x to the r. I think on the left-hand side, I'm just differentiating with respect to x. The ratio of, I don't know, what's another name for n?
R minus 1.
I can't.
Or R plus 1.
R plus 1. I just forgot. Short-term memory. What's another name for n? But doesn't this necessarily imply that if I want to integrate or anti-differentiate x to the r power, I up the exponent by 1, and I divide by the new exponent, and tack on my constant of integration. That is so important. I'm going to refer to this in my powerful anti-differentiation. Actually, do you guys think I can create a list? To anti-differentiate x to the n power with respect to x, I will up the exponent by 1, divide by the new exponent, and add my constant of integration. This from now on is what I'm going to refer to as my powerful anti-differentiation, or my powerful integration.
Bohemian Rhapsody very well specified to C.
I know it did.
You
It did
cannot
a good
forget to
job.
C.
So you can't forget it now.
No, you cannot forget
No,
to C.
no,
I'll
no.
never forget to C.
My question is this. Did they grab a track? from Queen for the music, or they did it themselves? It was too close.
No, it seemed like when you analyzed the video, when they were playing the instruments, they were just fake playing it. I didn't.
No, I know, but in terms of recording, what they recorded.
Oh, I think so.
You think what?
That they use the track.
You think Queen would allow that?
The what?
Do you think the group Queen would allow that?
I don't know, man, Freddie Mercury's dead, and
Half of them are
Bad
dead,
hasn't done it
and
in a while.
copy people.
Guys, do
copy
you think Queen would allow that?
No. Well, I'm
The
sure
group
the
Queen for-
the record label wouldn't.
Do you guys understand who the guitarist is?
Brian May,
Brian May, and he is now
astrophysicist or something.
with a PhD. He's just released his second book on the origins of the universe, as I recall. So my point is, I'm sure he'd be very happy to let somebody use that for a calculus song. I think.
Oh, I didn't know that.
I mean, I don't know the truth.
Although he doesn't have
As long as they're
any
not
say
making
in
money
it.
off
He
it.
would.
He doesn't have any say in it.
No, I'm saying maybe he did. Maybe they asked him for it. And if they did, I'm sure he'd say, "Oh, piece of cake."
Even if they asked him, he can't do anything. It's not his property anymore. It's the property of the record label.
Is it really? Did Queen give up those rights?
Welcome to American copyright law.
Oh.
Horrible.
No, I'm serious. I didn't think about that. I really didn't think about that. Interesting.
paid for it though.
You what?
Yeah, they get paid for it.
They get paid for it. It's like they sell it.
When they sign their contract, it's any music they make is the property of the record label.
I was just being a little goofy, suggesting that maybe with the guitarist being so math-oriented, he probably just says, piece of cake. Who's another math geek from music,
Oh,
pop culture?
I know who it is too, 'cause it's free.
Oh, I know, what about it?
I don't know.
Simon and
Garfunkel?
Garfunkel. Yeah, Garfunkel back to school. I think I got a graduate degree in that.
I heard the girl from the Wonder Years is like a math theorem.
Yes. Now I don't know how far she went. The last I read, she was finishing her bachelor's degree, but that's the last I read. But yeah, I forget her name. I don't know. I don't want to. Sorry, I'll come back. How about this? What if I were to anti-differentiate e to the x respect to x? What do I get?
Plus C.
Plus C.
What if I were to anti-differentiate a to the x respect to x?
Plus C.
Don't say that.
A over x plus 1, or a raised to the x plus 1 over x plus 1.
It's exponential, not power.
Oh, natural log. No? I don't know.
It's just.
Oh, natural log of A times,
I'll close my pen.
No, you're differentiating the
If
wrong
you
way.
differentiate a to the x, what do you get? A to the x times natural log of a. So going backwards, what do you do with the natural log of a?
Raises the x bar.
How about divide by both sides by it? Aren't you gonna get this? Just 1 over the natural log of a times a to the x plus c. What if I were to anti-differentiate 1 over x with respect to x? What would I get?
Natural log of x.
Does everybody agree?
Plus C.
Oh, sorry, this time I did forget that. That was my fault. Are you there? I'm not. I think there's a problem. Technically speaking, could x really be negative over here? If x is negative, is this fraction defined as a real number? Can I plug negative 5 in for x and get a real number?
Yes.
Yeah, it's just negative 1/5. Can I plug negative 5 in for x here and get a real number?
Nope.
Shoot, that's a problem. Can I take a break? Take a break. If I were to differentiate with respect to x, the natural log of x, don't I get this? But what if I were to differentiate with respect to x, the natural log of negative x? Wouldn't I get 1 over negative x?
No, you still put on the x.
What do you mean no? What's wrong?
It's absolute value of element.
I don't see any absolute
Element of
values.
absolute.
I don't understand where that came from. Don't I get this?
No, you told us we don't.
Would you apply the chain rule and say I gotta multiply by the derivative of whatever I was taking the natural log of?
Which is negative 1.
Thank you. Which, by the way, is nothing more than. Oh, you guys, check this out. To differentiate the natural log of x or negative x, I get the same darn thing. And so I think in undoing the differentiation process, to anti-differentiate 1 over x, I get the natural log of
Absolute
the absolute value of x. So I think I need the absolute value symbols in there. Are you with me? What can you say about anti-differentiating? I'm starting so slow, you guys. How about this? Do you guys think you can come up with just one function whose derivative is what's in the integrand's position?
Natural log of 1 plus x squared.
Say it again.
Natural log.
It's the inverse tangent. of x. David,
Oh.
do you agree? All right, as long as you agree. Well, there's one of them. Now let me give you all the others. What do you think you could say about undoing the differentiation process with this? Do you guys remember in 2 weeks from tonight we have a final?
Sine inverse of x plus
The inverse sine of x. Let's see. What if I were to differentiate with respect to x? 1 over a squared plus x squared. Isn't that the same thing as differentiating with respect to x? 1 over 1 plus x squared over a squared. Same thing, isn't it? Same thing, isn't it? What do you know? Why?
just looks weird.
Just looks weird. You know, you're right, I made a mistake. I think what I really did going from here to here, not that I differentiated, I was just playing with math skills. I think from here to here, what I pulled out was a factor of 1 over a squared. If you don't believe me, double check my work. Redistribute this back in. Don't I get a 1 over a squared plus x squared? It's just that this is 1 over a squared times the derivative with respect to x of 1 over 1 plus this thing squared. Inverse. Let's say it's still inverse tangent. And so I think, oh, you guys, I think I made a horrible, I really made a horrible mistake. I meant to differentiate the inverse tangent. I'm going in a completely wrong direction. I really made that blunder. Can I start that over again? What can you say about differentiating with respect to x? The inverse tangent of an x over a. To differentiate the inverse tangent of anything, don't I get a 1 over 1 plus that thing squared? Or can I say it differently? That would be a 1 over 1 plus x squared over a squared. Or shall I say, that's a 1 over a squared times 1 over a squared plus x squared. You guys okay with that? Everybody? Oh, come on, in harmony. No. Remember the final exam in 2 weeks? From here to here, what's wrong? There's something gravely missing. What is it?
No.
The constant.
Close.
Okay.
The chain rule.
Chain rule, yes.
Chain rule says I gotta multiply it by the derivative of what the heck I was taking the inverse tangent of, but the derivative of what I was taking the inverse tangent of is just 1 over a. And you know what? In the end, I think that has a big effect because now I think this, this business over here is going to have a bit of cancellation with everything else. As a matter of fact, yikes. I'm sorry, there's something wrong with that. What is it? Don't look at this last factor. You guys, I'm just bumbling with my algebra. If you look at this piece right here, if I rewrite it this way, what have I really done? Haven't I pulled out a 1 over 1 over a squared? Isn't it really I got from this circle to this circle? And double check, see if I made a mistake, because I'm full of them tonight. Go backwards. 1 over a squared times a squared is 1. But 1 over a squared times x squared is? Okay, I fixed my second blunder. Oh, by the way, there's a lingering factor of 1 over a. Of course, with a tad bit of cancellation, doesn't that leave me with this?
Isn't that just
Yeah, I agree. So I think this is nothing more than an a times 1 over a squared plus x squared. But you guys, I've done too much variety. Can I restate all this? I think what I'm really saying is this. What you see on the left-hand side. The derivative with respect to x of the inverse tangent of x over a is nothing more than my a times 1 over a squared plus x squared. Shoot, I still think that's complex. Let me simplify it.
A over
Yeah, I agree. I'll divide both sides by a. Can I get this? No tricks. But doesn't it give me this? Since this is just a constant coefficient, differentiating with respect to x, 1 over a inverse tangent of x over a is nothing more than 1 over a squared plus x squared. And if you guys are okay with my differentiation process, I think what that really means is that if I were to undo the differentiation process from here, that's exactly what I get. Let me write that more officially. I think what I wrote on the board was too limited when I wrote this. So, Giselle?
How did you get I squared plus x squared on the third line?
On the third line from here, 1, 2, 3.
Yes.
I'm kind of goofy. I sort of like said this. I want to pull out a factor of 1 over a squared from this term. But I don't see it here, so I'll cheat. And now when I pull out the 1 over a squared downstairs, a squared plus x squared is what's left over. Did you see it, Giselle? Okay, let me do something else then. From here to here, is that okay? If it is, can I write a squared over a squared as black a squared times red 1 over a squared? Same thing. Yeah. And let me take a peek at the x squared over a squared. I think it's a black x squared times 1 over red a squared. And so if I pull out the red 1 over a squared in black, here are the remaining factors from those two terms on either side of the addition operation. Do you see it? That's all I did. I just pulled out a funky looking factor of 1 over a squared. So everybody, let's make this official. I think as an extension from this mathematical statement here, I've just proven that the antiderivative for a squared plus x squared with respect to x, at least a general antiderivative, is 1 over a inverse tangent of x over a. If I took the time, I can likewise show you using exactly the same logic that antidifferentiating the square root of a squared minus x squared with respect to x simply gives me the inverse sign of x over a. Oh shoot, I forgot my constant of integration. Using the same logic.
What happened to the 1 over a in front?
Because of the square rooting operation, there's no e's left over. Instead of getting it a 1 over a squared down here, it's just a 1 over a when I pull it out, and it cancels with that 1 over a. Oh, I don't know, you guys, any other basics with which I need to state? I think this is just a subcase of the first particular rule I had over there, but what can you say about the antiderivative of some constant k with respect to x? What do you think you get?
A plus
K times x plus c. Maybe I just wasted 15 seconds of your life. Technically speaking, this is just a subcase of this particular statement over here, where n is equal to 0. Now, would you guys agree that if I were to differentiate with respect to x, a constant times a function, that's just a constant times the derivative function? That was a yes or no response.
Yes.
Yeah.
Yes.
Well, if constants get pulled out of the differentiation process of coefficients, then certainly when I anti-differentiate, constants here too will get pulled out of the integration process. I want a yes or no response. If I were to differentiate with respect to x, the sum or the difference of two functions, wouldn't that give me the sum or the difference in their derivatives? Yeah, I agree, which kind of suggests that when I undo the differentiation process, that it should be the case that the antiderivative for the sum of these two functions, or for the difference with respect to x, really should give me the sum or the difference in their individual antiderivatives. Do you guys think I could just rattle off the next two that I really want to list? For example, the antidifferentiate the product of two functions. That's merely going to be the product of their antiderivatives. or maybe to anti-differentiate the ratio of two functions. That's simply the ratio of their antiderivatives individually. So you guys, can I start talking about some specific examples? Are you ready?
Good.
Sir, for specific examples.
Absolutely not.
Good, I'm not ready either. Why not? No, I think there's another reason. Why not?
Talk about.
How about this? If I differentiate the product, is it the product of individual derivatives? If I differentiate with respect to x, f of x times g of x, does that give me the product of their individual derivatives? What do you mean, no, why not? Oh, you're right, to differentiate the product of two functions, I think it's a much more complex operation. I guess something called a product rule is nasty business over here. That kind of suggests that maybe when I anti-differentiate a product, I do not get the product of the antiderivatives. Life is not that smooth. Likewise, if I were to differentiate the ratio of two functions, don't you guys agree it's nasty business? It's called the quotient rule. It's not the ratio of the derivatives. So I think in undoing the integral of a ratio of two functions, here too, you guys, there's no way I should get the ratio of their antiderivatives. I think integration as an operation distributes over addition, subtraction, and maybe scalars get pulled out as coefficients, and that is about it. To handle nasty business like this or this, that requires math down. 31. 31. We'll devote a lot of attention to dealing with integrals of products and ratios. For now, I'm very restricted. As of tonight, I've only got these two sophisticated properties, beyond the ones I've already got listed. So, now I think I'm ready to do some practice. Yeah. Good, I'm glad you agree. So you guys, an hour and 45 minutes in the class tonight. I get to get to my first example. Aw, look how nice and easy that example is.
Yeah.
Now, I think the integral of a sum or difference is a sum or difference of the individual integrals. Constants get pulled out. I'm going to skip all those steps. Using the power of integration, what do I do with that exponent?
Add 1.
Add 1 to it, and then
Divide
by the new exponent. Plus,
Add 1.
add 1 to the exponent, and then divide by the new exponent. Plus, or excuse me, in this case, minus.
That's it.
Plus C.
Thank you. That plus c means I get an infinite collection of functions that are the antiderivatives of the function in Lagrange position.
Yeah, I was gonna ask if we forget on the final, how much is that?
I'm so sorry,
That's
guys.
okay. How much? How much is that gonna actually dock us?
10 points.
Well, if this were a 10-point question, I wouldn't take up more than 8.
We think he's joking.
This is a serious phase.
At minimum a point. At minimum.
Okay.
Maybe you guys hear me with this?
That's only half of your local extreme.
You guys humor me. To anti-differentiate x cubed, what do I get?
Nothing.
The answer to x cubed is...
X to the 4 over the 4.
X to the
How about nothing? Because if I'm going to integrate, a ratio is not the ratio of integrand. I can't handle a ratio. And since I can't handle a ratio in integrand's position, maybe we should just give up math 30 and apply math, what's your favorite math class? Math? D. And massage the expression in integrand's position first. I think that's just an x squared over root x. I misspoke, didn't I? I meant x cubed over root x plus an x squared over root x minus an x over root x plus 3 over root x.
Just let him go all over you.
Oh, the bubbles are killing me. You guys, I'm sorry for the phone.
It's okay.
You know, the phone's only ringing because of bubbles. If there were no bubbles, it would
Can we turn off the projector?
You can turn off the projector.
Blank. Should be a blank.
If you insist.
Wow.
It's too simple a
Take your
solution.
logic
I
out.
wanna apply some calculus.
No, Matt B.
Get that simple logic out of here.
Aw, you guys humor me. Matt B. Very nice. That is so nice. You guys have expressed each and every one of these four terms as a power term. Now I get to use my power over anti-differentiation. All I have to do is come in and up my exponent by 1 and divide by the new exponent. Here too, up my exponent by 1 and divide by the new exponent. Here too, up my exponent by 1 and divide by the new exponent. And finally, up my exponent by 1 and divide by the new exponent. What's missing?
Let's see.
Are you happy?
Yeah.
Are you really happy?
No.
No, because you're still writing. I'll close my pen, okay? But I'm still unhappy because, you know, sir, you've got a good point. If I had an individual fraction, mathematical etiquette suggests maybe I should write it as a single fraction. It's just in this example, in the end, I don't have any fractions. But nevertheless, mathematical etiquette suggests I should. No, I think just rewrite in terms of radical expressions. So, let's rewrite. I think what that leaves me with is 2/7 times math B. Math B. The blood's all rushing down my arm. I'm going numb, I'm gonna faint. Oh, that's what you want, isn't it? X.
Squared. To the 4?
I feel like you're a random number generator.
One.
Root squared.
It's the smallest odd prime.
Nothing.
It's the smallest odd prime. No.
Oh, it's 3.
3.
I don't know what's going on.
I'm trying to convert fractional exponentiation to radical notation using my math D skills. Thank you, thank you. Oh, we're on such a roll. Oh, plus 2/5 times. I did walk in the right classroom, didn't I? I gotta check.
No, this is not D.
Sometimes we wonder ourselves. Because it's just, you know, class.
Minus
2/3.
2/3
Yeah.
x. Oh, this is painful. Plus. Now, you guys, isn't that much more aesthetically pleasing to the eye? It's back in terms of the original notation being used. Don't you all jump up and say yes at the same time.
Yeah.
Yeah, that's what I want to hear.
You have to open the classroom.
Yeah, that's right. Because I want to. Because I can. Where'd you get the negative?
Well, it has to be negative because sign's positive.
I like this better. Why are you saying I'm wrong?
Yes.
Well, yeah, because
I am
then it would be
wrong.
negative.
Because I think to differentiate cosine of x, I get
Negative sign.
sine of x, which means if I anti-differentiate sine of x, I should get negative cosine of x. Oh, we are on a roll.
Sine of x.
Natural log of x.
Tangent.
Secant of x.
Plus
Plus
C.
C.
Yeah. Just happy.
Are you there?
Mm-hmm.
No.
We're getting there.
Oh no.
Yes. Calculators.
You
Go.
really should see come with these calculator regressions.
Like, what if there's somebody walking past and you just huck a calculator at them?
Okay, what if you threw a calculator off the Empire State Building? We'll get
I want to just fly back up. Thank you. Resistance would like send it right back up. And then it'll fly up like this, and some go down.
It'll hit you right back because it's inverse, so it'll fly right back at you.
Everything's ready for summer. It's turning clouds.
That's a strong arm right there. Goodness.
So everybody, I want to find out, I'm going to ask a few questions. Number one first. Determine the velocity at which my calculator changes position. What would that be in this case?
1/2 mv squared plus mg.
Negative 16.
Would you get negative 16?
That's the gravitational constant feet.
Ooh, I like that. Let me start where he's at. He's basically saying this. If you look at the acceleration of my calculator over time t, I think in this particular example, it's going to be nothing more than the opposite of the gravitational pull for this particular planet. Which means, to undo the differentiation process, to anti-differentiate, I will get a velocity function with respect to t. And does everybody see my independent variables t is g? Come on, everybody.
Yes.
No. That's just a constant. My independent variable is t. So anti-differentiated constant, what do I get? Negative g times that variable t plus
C.
a constant. Can I call it c1?
Sure.
Oh, you know what, you guys? I don't like this. Actually, if you take a peek at what I really have, I've got my v of t being equal to negative g times t plus c1, where I think the initial velocity was given as 48 feet per second, 48 feet per second, if I can say it. But that means when I take this equation, substitute 0 for t, and simultaneously substitute 48 in for v, doesn't that give me this? Oh, but that suggests that maybe my velocity after time t is given as negative g times t plus my constant c1, which is 48. But since velocity is a derivative of position, then maybe my position, or in this case height function, can be generated by anti-differentiating this function with respect to t. Doesn't that give me a negative 1/2 gt squared plus 48t plus another constant c2? Where I confess it is the case that the initial height is equal to 64 feet. But that suggests that when I plug 0 for t and simultaneously 64 in for h, I get this equation. 64 is equal to 0 plus 0 plus c sub 2. Shoot, that means that h of t is equal to negative 1/2 times g times t squared plus 48t plus my constant c2, which is 64. Ah, shoot, you guys help me with this. Don't we know what g is? Isn't it just simply, was it 9.8 meters per second squared? Everybody.
Yes. Negative 9.9.
Negative. No.
He's got the negative there.
No, why not? Because we're using British units. Since I'm using British units for my initial height and my initial velocity, I guess I'm wrong. Instead of using 9.8 meters per second squared, I should use
32 feet.
32 feet per second squared. Negative 1/2 of that is negative 16t squared plus 48t plus 64.
That's fancy.
It is fancy. As a matter of fact, you guys, if I were trying to beat the clock, maybe I should have said this. If the initial height is called h sub naught, and the initial velocity is called v sub naught, using exactly the same argument, anti-differentiating step by step, I think I find out that the height of my calculator, t, is equal to negative 1/2 times the gravitational pull for this particular planet, times t squared plus my initial velocity times t plus my initial height. Which, by the way, is exactly what I have here. That's the initial velocity, that's the initial height. And so, I know you guys have seen this back in physics. It's just that finally took me the entire semester, but I finally proven to you